Click the bell icon to get latest videos from Ekeeda.
Hello friends, in this video we are going to learn about sun control films and how we are going to use the principle of interference of light to produce a sun control film. What do you mean by a sun control film? A sun control film is a film in which the transmission has been reduced and the reflection has been increased. And how do we do that? We do this by monitoring the thickness of the thin film and the refractive index of the thin film. This is how we do it. Consider a ray of light, AB, incident on a air film interface. This is our sun control film, which is deposited on glass. So when this ray of light is incident at the point B, two things are going to happen. First, there is going to be reflection in the direction BR1, and there is going to be a refraction in the direction BC. At the point C, once again, there is going to be a reflection in the direction of CD, and at D, there is going to be a refraction in the direction DR2. And if at all I want to make a sun control film, then I shall see to it that the intensity of BR1 and DR2 is maximum. That is, they interfere constructively. And for this, let us consider the basic concept of optical part difference between the two. The optical part difference between the two is delta is equal to 2 mu ft into cos theta, wherein mu f is the refractive index of the film, the sun control film. T is the thickness, the value of which we don't know now, and theta is actually the angle of refraction, which for normal incidence, that is, if I is equal to 0, your theta actually becomes equal to 0. So from this basics, what we do is we actually try to find out what value of thickness will be required in order for a film to act as a sun control film. Here is our equation for the optical part difference. But what we have not taken into consideration is the reflection of the rays from materials whose refractive index was actually greater. And hence the optical part difference delta is equal to 2 mu ft into cos of theta plus or minus lambda. As we already stated that in a sun control film, we want the transmission to be less and the reflection to be more. This means the reflected rays which are there, both of them should interfere constructively. For this, once again, let us have a look at the basic diagram. So what I want is the ray BR1. So what I want is the ray BR1 and the ray DR2 should interfere constructively. Going ahead with the derivation, delta is equal to 2 into mu f into t into cos theta plus or minus lambda. I want this to be an multiple of n lambda, because in this particular case, you are going to have constructive interference. We can now simplify this further to give you 2 mu f into t into cos of theta is equal to n lambda plus or minus lambda. And hence, this can be equal to t, because remember, what we want is the expression for the thickness. So t is going to be equal to n plus or minus 1 into lambda divided by 2 into mu f, and there is a cos theta term that is coming. But as we know that if your I is equal to 0, even your theta, the angle of refraction, will be equal to 0, and hence your cos of theta will turn out to be 1. Hence this expression will now turn out to be t is equal to n plus or minus 1 into lambda divided by 2 into mu f. Just for a simplified purpose, we consider that let n plus or minus 1 is equal to a number m. Thus, we can write your T is going to be equal to m lambda upon 2 into mu f. And thus, what we get from here is the thickness should be an integral multiple of the factor lambda upon 2 mu f. And if that occurs, then the coating of the film, and this coat, mind you, is on the glass, this particular coating will act as a sun control film, diminishing the transmission and enhancing the reflection. So far so good. So we have obtained an expression for the thickness of the sun control film. As usual, there are two parameters that will actually govern the action of a thin film as a sun control film. One is the thickness and the second one is the refractive index of this particular film. Let us now have a look as to what should be the value of the refractive index of this particular sun control film. When we are studying the values of the refractive index of the sun control film, what we need to understand is the amplitude of these two waves. The amplitude of these two waves, that is BR1 and DR2, they should be equal. And for that to occur, we are actually taking help of the electromagnetic theory and we are actually equating the squares of the amplitudes. Thus, we have mu f minus of mu a divided by mu f plus of mu a, the whole square is equal to mu g minus of mu f divided by mu g plus of mu f, the whole square. This condition ensures that the amplitude of the two reflected waves are same, wherein mu f is the refractive index of the sun control film, mu a is that of the air medium, mu g is the refractive index of glass. I simplify this still further and I get mu f minus of mu a upon mu f plus of mu a minus 1 is equal to mu g minus of mu f upon mu g plus of mu f. I perform the same operation on this side. Mind you, I can actually cancel off this one. Mu a is 1, the refractive index of air or vacuum, for example. So that is going to be equal to mu f minus of 1 divided by mu f plus of 1 minus of 1 is equal to mu g minus of mu f divided by mu g plus of mu f minus of 1. This can now be simplified still further. And how do we do that? This will be equal to mu f minus 1 minus of mu f minus of 1 divided by mu f plus 1 is equal to mu g minus of mu f minus of mu g minus of mu f. This entire thing will be divided by mu g plus mu f. Certain parameters are now going to get cancelled out over here, which are going to simplify our expressions. And this is how it's going to be. And hence, it's going to be equal to minus of 2 upon mu f plus 1 is equal to minus of 2 mu f upon mu g plus mu f, which I simplify it still further, to give you minus of 2 mu g minus of 2 mu f is equal to minus of 2 mu f square and minus of 2 mu f. Once again, we are going to get some certain calculations out over here, some cancellations over here, and I'm going to write down out over here that the only two parameters that are remaining are these and these. And this will turn out to be, this means I'm just putting it right over here, right on top, the condition that we are actually getting. And that is your mu g is equal to mu f square, which I can very well write it as mu g is equal to mu f. So this is the condition for the refractive index of the film. Typically, the values of mu g is 1.5 and the value of the film, if at all I'm taking, let us say, the square root of this one, is going to be equal to approximately 1.22. So the material that are going to fit in this particular condition are magnesium fluoride, which is near to that, the refractive index 1.38, or that of cryolite, mu is equal to 1.36. So these are the materials that we can use as a coat for acting as a sun controlled thin film over glass. And of course, we have to also monitor the thickness so that it is an integral multiple of the factor lambda upon 2 mu f. So we have obtained the condition for the thickness as well as we have obtained the condition for the refractive index of the sun controlled thin film. Sincere thanks students for watching this particular video. Stay tuned to Ekeeda and do subscribe to Ekeeda. Thanks a lot.